Welcome, my dear students. Today we studied the measurement of lowering of vapor pressure, static and dynamic method. The lowering of vapor pressure is small and hence it is not possible to measure the vapor pressure of the solvent P raised to 0 and solution P separately. And the difference obtained the lowering of vapor pressure delta P. The lowering of vapor pressure can be determined generally by two methods, static method and the dynamic method. The barometric method is neither practicable nor accurate as the lowering of vapor pressure is too small. The lowering of vapor pressure of a solvent when a non-volatile solute is dissolved in it can be measured by static method or the dynamic method. We learn that static method. To measure the directly lowering of vapor pressure, a differential manometer is used. In this method, a differential manometer consisting of U-tube containing a liquid, a manometric liquid, or the manometric indicator liquid of low volatility and low density, or the inert non-volatile, that is the monometric liquid. Example, the N-butyl phthalate or beta-bromophthalene is commonly used as the monometric liquid. The mercury is also a monometric indicator. The apparatus consists of a differential manometer which consists of U-tube. A glass bulb is attached to each arm of the U-tube. There are two taps T1 and T2 attached to the vacuum pump. One arm of the bulb is filled with a pure solvent and the other bulb is filled with the solution of the same solvent. The taps T1 and T2 are open and the air inside the apparatus is removed by the vacuum pump that is connected to the taps. The difference in the vapor pressure is determined directly from the difference in levels of the indicator liquid in the two arms of the U-tube is read off with the help of moving telescope. This gives the difference between the vapor pressures of the pure solvent and the solution, means P raised to 0 minus P. The difference between the vapor pressure of solvent and the solution is determined with the help of the differential manometer, and the thermostat is used to maintain the temperature. The another method, that is the dynamic method, Ostwald-Walker's dynamic method, or it is known as the gas saturation method. In this method, the relative lowering of vapor pressure can be determined straight away. Dynamic methods have been more extensively used and are easier to handle. In this Ostwald-Walker method, a stream of fixed volume of dry air is passed through a series of bulbs, that is the glass cylinders, containing the solution and through the pure solvent and finally an absorbent to absorb the vapors of the solvent. With the aqueous solution, anhydrous calcium chloride is used as absorbent. As dry air passes through the solution, it becomes saturated up to the vapor pressure of the solution. The actual loss of the vapors from the bulb glass cylinder is obtained by weighing them before and after the air has been passed through them. The loss in weight or mass of the solution is proportional to the vapor pressure of the solution P. Means the loss in mass of the solution delta W1 is proportional to the P. The air already saturated with the vapors of solution P is then passed through a series of previously weighed bulbs, glass cylinders filled with a pure solvent. The air further takes up more vapors from the pure solvent that is vapor pressure of pure solvent P raised to 0 is greater than that of the solution P. Means there is in a bulb unit, there is a saturated up to pressure P raised to 0. The bulb are weighed again to obtain the loss in mass delta W2, which is required to saturate air from pressure of P to P raised to 0. That is, a delta W2 is proportional to the P raised to 0 minus P. Finally, the air is passed through a set of weighed U-tubes containing the absorbent for the vapors of the solvent, that is for the vapors of the pure solvent. Example, anhydrous calcium chloride is used as absorbent if water is used as a solvent. The increase in mass of the U-tube is determined. It gives the total loss delta W1 plus delta W2. The loss in mass gives the measure of the vapor pressure required to saturate air up to vapor pressure P raised to 0. Means vapor pressure required to saturate air to P raised to 0. P raised to 0 minus P upon P raised to 0 is equal to delta W2 upon the delta W1 plus delta W2 is equal to the loss in mass of the solvent, in bulb B divided by the gain in mass of calcium chloride tubes. Means their loss in mass of a solvent upon the gain in the mass of the calcium chloride tubes. The amount of solvent taken up in a set of bulb A solution is proportional to P, and the amount taken up in a set of bulb B solvent is proportional to P raised to 0 minus P. If W1, W2 be the loss of weight in a set of bulb A and the set of bulb B respectively, the W1 is proportional to the P and W2 is proportional to the P raised to 0 minus P. Adding W1 plus W2 is proportional to P plus P raised to 0 minus P. Then W1 plus W2 is proportional to P raised to 0. Means P raised to 0 minus P upon the P raised to 0 is equal to W2 upon W1 plus W2. P raised to 0 minus P upon P raised to 0 is equal to W2 upon W1 plus W2. We write there the W2 instead of that delta W2 or delta W1 also. The gain in mass of calcium chloride tubes is equal to W1 plus W2. Gain in weight is proportional to the P raised to 0. Then the loss in weight W1 is proportional to the P for set bulb A. Loss in weight W2 is proportional to P raised to 0 minus P for set bulb B. And gain in weight is proportional to P raised to 0. It is for the U-tube. The knowing the loss of mass in set bulb B W2 and the total loss of mass in the two sets bulb A and bulb B W1 and W2, we can find the relative lowering of vapor pressure delta P upon P raised to 0. Here the knowing W1 W2, the relative lowering of vapor pressure can be calculated. Thank you.